And we don't even get to see what the point of the video was. I was supposed to be a melon cover of Smash Mouth's All Star. Anyways, good morning. So there's still a week until this assignment is due, but I figured that probably by now most of you have taken a look at it. So if there's any good time to give some hints and advice, now is probably the best time to do it. So just a quick overview and some extra tips in case you're stuck, or even if you haven't looked at it, just to set you on the right path. So one is just doing the scope and variable that we did in lecture. Two is translating some sentences into predicate logic. I just posted some extra questions um, last night in the announcement. So by doing those and doing the ones in class, you should be able to do most of these. There might still be a little bit of a challenge thinking about these two. So for D, I gave a little hint here. And for C, think about how we did adjectives. So it's not just as simple as saying and with one predicate, but it follows a very similar pattern. So um, every robot who takes an order, every order taking robot. So you have to figure out how to deal with taking an order, since that is another predicate and an order is a noun phrase, but it works similar to how adjectives work. Um, and then the rest are things that you've seen before. Three. Three has given people trouble in the past, so I use letters and numbers here, and this looks a little bit different, but this is just like what we've done in class. So in class, we saw stuff like Mary slash X2. Here, I'm just simplifying it a little bit, and I'm doing things like L slash 5. But the notation, uh, it still aligns exactly the same. Instead of using like an X, I'm just using a number. And instead of using a full name, I'm just using a capital letter. The reason I'm doing this question like this with just numbers instead of variables is because sometimes in semantics, they just use numbers instead of X's. So um, when you have G's, sometimes even the notation is literally just like 1 to Mary and 2 to John, rather than things like, John slash X2. It depends which book you read, and it depends what types of papers you read. So just to expose you to both, this is what that question looks like. And this little number in the brackets here, again, is just like what we saw in the practice is what you're evaluating. So what is the value of 4 after making those changes? What is the value of 5 after making those changes? So in this one, if we said G of Mary, G Mary X2, and we're checking what X2 is after, we'd say that's Mary because we've replaced Mary with whatever was in X2. Question 4 is a little bit more involved. So here I'm giving you a bunch of information about a world. We use V as a function to give us situation information. Um, and then you're evaluating the truth of these statements. So this V here stands for vowel, not the function itself. So I wrote that down. And then for B, you're just translating these into predicate logic using these different predicates. So using like A and C and V and B and N. So all of these predicates are already defined for you, so you don't need to come up with anything new. You should be able to translate all of these sentences 1, 2, 3, and 4 with the things above. Now, one hint is that 4 here is a little bit difficult. That's why it's the very final question in learning and reinforcement, because you will have to use the not equals operator. For a for question 4 before 4a and 4b is just information. Yeah. So all this stuff is just information. So we're saying that like the letter M is just M, the letter N is just N, and then A means that X is a letter in U. C means that that X is a consonant in U. So these are just like defining the predicates. So if we say like A M, this is saying like M is a letter. And yeah, that would be true because M is a letter. But if we said like A of 1, that would be false because 1 is not a letter. And then this one is saying, okay, anything that C is a consonant. So yeah, C of B is true, but C of A would be false because A is not a consonant, A is a vowel. And then we could do the same with V, and then B and N are two-place predicates. So B is about what occurs before in the alphabet, and N is about what's near something else in the alphabet.
I don't quite understand what you should do for question 3.
Sorry, can you repeat that? You cut off at the end of the question.
Yeah, so I don't quite understand what you should do for question 3.
For question 3,
Yes.
so for question 3, this is just an assignment function replacement. So you're saying like here in the description, we've established what 1, 2, 3, 4, and everything above 5 is. Here we're making replacements, and then you have to evaluate like what is 4 now after these replacements? What is 5 after those replacements? What is 6 after those replacements? And what is 7 after those replacements? So you're just telling me like what the letter is after we've made all those substitutions. So it's just like when we did all those name replacements with like Mary, John, and Rufus and Pete, and then we asked like who is X3 when we replace uh, Pete on X3 or Sam on X3. It's the same sort of idea, but we just have numbers now.
So the answer should come out as the alphabet.
Yeah, one of the letters of the alphabet.
Okay, thank you.
Okay, for understanding an extension, um, I try to lead you in with question A about what things should look like. So basically, we're adding some new rules. Two of the questions are very similar, question 5 and question 7. So uh, question 5 says, well, we've been treating these predicate adjectives is happy as VIs, but that's not very satisfactory to linguists because happy is an adjective. So happy should be an adjective and it should be treated as an adjective. So um, we can give it its own category, and you have to figure out what happy should be in terms of sets. So I say, okay, well, what is happy in predicate logic, and use that as a base. And also I tell you what we want the VP to be. So you're going to find that the VP and the adjective are very, very similar, and that's a major hint. And this is a problem for is. You're going to see why that's a problem for is, because if happy and the VP are very similar, then what could the meaning of is be? Well, is something that is semantically vacuous. So this just means that is has no meaning. It's just like an equals. It just assigns whatever's after it to whatever's before it. Um, so this is going to be one of the first nodes in our tree that just don't get a value, at least in our version of semantics. So you'll have to figure out what the rule is to get the adjective, to get the meaning of the VP from its two daughters here. And you'll have to do the composition on the tree after that. And it will be the same for question 7. What I will say about question 7 is that we've been talking now about movement, quantifier raising and things in F2. This is not F2. This is still F1. So we do not have quantifier raising. So even though we see a linguist here, do not quantifier raise in this case. This is not F2. This is still F1. So leave a linguist where it is. Leave a linguist where it is. If you move it, it's not going to work, and it's going to overcomplicate things. So I guess this is sort of the unfortunate side of having this assignment too after we talk about F2. Um, but yeah, uh, very similar to the question before. Question 6, we didn't talk about the conditional for our values. And really, we shouldn't be talking about the conditional because the conditional requires possible worlds. It requires a little bit more what we call intentional semantics or modality to do it. Um, but we can think about how it could be done because we know an equivalent translation for P arrow Q. We know we can do it as not P or Q. So using this information in this question, you're really just going to give the values of the when matrix, the conjunction matrix, and what the sentence should look like. When we take the sentences, Sarah is happy when Sarah meets Kathy. What I do want to say for this one, though, is that remember that when we translate a sentence, one side is the antecedent and one side is the consequent. That matters. So when we have ordered pairs in our little matrix here, the ordered pair matters. So if we have like S1 and S2, S1, well, I guess, let me change this. S2, S3. The first one is S2. The second one is S3. And that order is consistent. So when you're figuring out the truth table for this matrix, S2 is on the left, S3 is on the right. So keep that in mind when you're figuring out like 1, 1, 1, 0, 0, 1, and 0, 0, and which one is true and which one is false. That's my hint for that one. Do you know which day the name replacement part of that lecture was? May need to rewatch. For the assignment functions, that was last class. That would be, no, that wasn't last class. That was the class before. That was predicate logic 7.4, I believe. Last Friday. Yeah, the assignment function should have been in the very last predicate logic lecture. Okay, again, you can always ask me anytime about these assignments, but are there any remaining questions that you have about assignment 5 that I didn't cover or do you just want more explanation about? Okay, and as always, for questions 5 and 7, even if you aren't quite getting there and you ask questions or don't ask questions, just give it your best attempt because these questions aren't always uh, easy to figure out. So what I'm just looking for are your ideas, and giving it an attempt will always at least get you some partial marks on these questions because they are tough, just like the ditransitive question from last week or last assignment. So anyway, let's go back to ye old rules. So let's just refresh this rule a little bit because it's been a couple days for some. So this sentence was this was some student, and that was 1, and this was T1 likes Kier. This was the sentence that we were looking at. And the idea was like, how do we figure out what its truth condition is? So if we take a look at just the sentence T1 likes Kier, this would be true if the assignment function for g of T1 is in the set of x such that x likes Kier in M. So if we just had like a word like Kayla here, we would just have like k prime in here, and this would look just like we had before. But now we have a trace here, so we have this g of t1. But it's really just the same as what we've done before. Now, some student is a quantified noun phrase, so this node won't actually get a meaning associated with it, because with the quantifiers we have to dig a little bit deeper, and it's used as a unit to figure out the rule. Um, so when we go up, again, we're really abusing that predicate logic notation. So we're using the fact that we're going to translate this as exists in X, student X, and like X here. So if I write it out like this, we can sort of see things piece by piece. So for some D in our universe, so this is like that exists in X portion, D is a student. So we're saying that X is a student in that case. And our original sentence, T1 likes Kier, is true. So this is T1 likes Kier, but we're doing binding, replacing all of our T1s with D. So with that student. So when we spell it out, we get for some D in our universe, D is in the set of X such that X is a student, and D is in the set of X such that X likes Kier. So in other words, here we would have the binding happening between the student being X and the student being the person liking Kier. And because we're looking at the existential sum student, we're using the existential exists in X. And of course, existentials come with ands, so we use our conjunction here. So I think it's good to see it in action in our trees, but before we see it in action, that was just a quick review. But are there any questions about the universal and existential now that you've had a few days to think about these? Okay. So let's see a tree, and I will be zooming in quite far because the slides are quite dense. I tried to fit everything in on one slide, and just because of that, the text is quite small. So I apologize for that, but it either looks pretty and small or it looks very gross and very big. So unfortunately, I chose the pretty route. Okay, so oh, I should probably say what the sentence is that we're looking at. So we're looking at the sentence that we started with at the very beginning of the lecture, which is Sam saw a movie. And this is the one that we drew the syntactic tree for, and we had the translation for. So Sam saw a movie, and predicate logic is there exists an X such that X is a movie, and Sam saw X. So our predicate logic translation is going to match our truth conditions at the top. And we'll see that in action. So let's start at the bottom right of the tree. And what we're going to notice is that our first sentence bit, uh, Sam saw a movie, is going to look very similar to things we've already done. So the first thing we notice, and actually let me just zoom out for this first part to remind you, is that a movie is a quantified expression. So this a movie is being moved into a higher position outside of that original sentence. So we get a movie, Sam saw T1, and T1 is replacing a movie. So we have the one up here to say it has moved, and then we leave the trace in its place. So movement has occurred there. Now, when we go back in here, that means that we're going to start our semantics with evaluating T1. So when we evaluate T1, again, we're not checking to see specifically what T1 is pointing to at the end. We're just saying, okay, the meaning of T1 is just G of T1. So uh, we'll let the assignment function take care of it at the end. Okay, when we go up to the noun phrase, again, it's just going to take a look at its kid because it only has one child. So it'll just take the same meaning, which will be G of T1. Okay, if we want to know what the meaning of the verb phrase is now, we have to take a look at both of its children. So we need to take a look at saw. So saw is a transitive verb. So we're looking at pairs of x, y, where x saw y and m. This is going to go up to our transitive verb VT for the same thing because it's got one kid. And now, when we go up to our verb phrase, it's looking the same as before. We're taking our uh, object, in this case, it's the noun phrase, and we're substituting it in for the object position. So when we take a look at our pair, we're now just looking for subjects. We've substituted in our noun phrase for that y position, and we evaluate it now as the set of x, such that x saw g of t1 in M. So instead of having a proper name there, like we would before, now we have a trace. But same process as before. So the rule hasn't changed. It's just what it looks like has changed because we have a function there instead of a name. Now, if we complete the rest of the sentence with Sam as our subject, so Sam saw T1, well, Sam is a proper name. Now we have this extra middle node because we need to specify that our noun is specifically a proper name instead of a common noun or a pronoun. So we have this middle tier. In fact, I made a little bit of a mistake here. I really should have the rule here if I want to have every detail involved. So I should have that there, which is Sam. Then moving up, I have the pronoun to fill the NP. And then the sentence rule again is just the same. It's true if the noun phrase is an element of the verb phrase. So if Sam is an element of the set of x, such that x saw g of t1 and m. So we've now successfully constructed exactly what we constructed in an F1. Except now we have g of t1 instead of a proper name. But everything we've learned before has carried over, which is really nice. So in terms of like the logic, the predicate logic, we've essentially constructed at this point saw Sam X. This is really what we've constructed at this point. So the X hasn't been bound. It's sort of like a pronoun. We don't know what X is. It's like saying Sam saw it, but we don't know what it is according to the tree yet, because we don't know a movie at this point. So at this point, we're going to take a look at the left side of the tree to get a movie. And unfortunately, there we go. Let's take a look at the left side and let's see what we're labeling. So this whole bit will act as a unit together in order to get a rule. So we're not going to label the meanings of a, d, or the NP. The system just doesn't have a nice way of handling that. So these nodes will be empty. D stands for determiner. In some courses you'll see DET for det, but usually you'll just see D. So you can let me write it in a thinner color. Determiner. So usually you'll just see D. So we can write the things for movie and our common nouns. So we know that we know that any common noun is a predicate. So for movie, we can write like the set of X such that X is a movie. And we can then send it up to the common noun, and we can say that the common noun then would be movie, which is the set of X such that X is a movie in M. So we could do these two nodes. And this is helpful because when we look at our rule above and we apply the quantifier, we need to say, well, what's in our common noun? We need to know that information. So we can do these two, but that determiner line on the left and that noun phrase itself, we can't quite give a meaning to. So once we fill that information in, then we can take a look at S2. So S2 is now just an application of the rule that we saw before in that previous slide. So we write out the rule. And at this point, let me get red smaller so I can use red. So now we're going to do binding. So basically, we're going to do the existent X such that movie X and we're going to connect it with saw Sam X. So we're introducing that existent X to bind it. That's what this next step is doing. So now we're going to say it's true if for some D in our universe, so this is where the existential's coming in, D is in our common noun, and the remainder of the sentence that we did before is true with some binding. So T1 here is being bound, and we know that T1 is being bound by checking to see which noun phrase we're connecting. So because we're connecting NP1, this means that we're going to bind T1. If we were to do NP2, then we would bind T2. So the NP that we're dealing with is telling us which trace we're going to bind. So when we then spell this out, we just break down each part piece by piece. So for some D in our universe, D is in the noun, in the common noun. So D is in the set of X, such that X is a movie in M. Okay. That's just breaking down the common noun. In fact, we're just really stealing it straight from the common noun here. And S1 is true where all the G of T1s. So what this is really doing is we're saying now all the G of T1s are now just D. So we're taking this line here, Sam prime is in the set of X, such that X odd G of T1. We're bringing that up, except instead of having G of T1, we now have D. We've made the replacement there. So and Sam is in the set of X, such that X odd D in M. So yeah, I'm sorry for there's a lot of marks on this page. I know it looks quite messy at the end. It's just a lot of small things to point out. So D replaces the trace. What does the lowercase d mean? D is just a variable. So when we talk about our universe, which is full of like a million different things, we just need something to run through everything in the universe to check. So it's sort of like saying, okay, first we're going to check this. So we're going to pretend D is that and check that. And then we're going to pretend D is this and check that. Then we're going to pretend D is this and check that, and then check that, and then check that. So we could use any letter we want. It's just convention to use D. Like normally we might want to use something like X or Y because that's what we're used to. But the problem with using X and Y is that we've already used X. And sometimes we use Y, and sometimes we use Z. So by picking D, we're using a letter that we probably haven't used already. Okay, so just to make, sorry, I'll zoom. That's way too far. There we go. So just to have that comparison on screen with the predicate logic translation again, and the final line here. So let me just get rid of these lines. So you have there exists in X. I guess I already rewrote it below. But again, exists in X, movie X, and saw Sam X. So we have that exists in X. So if for some D in our universe, D is in the set of X such that X is a movie, so that's movie X. We have the and then we have Sam is in the set of X such that X saw D. So we have our predicate logic translation matching with our truth conditional semantics like perfectly there. So you'll probably have to go through the tree again a couple more times just to inspect everything, especially when you're doing your um, assignment 6. And when you do the practice on the Canvas page as well, for sure you'll have to reference the tree a couple times. Just an initial run through. So again, just to remind you of where this stuff is. There's not a lot of practice for these, but the first couple examples will help. So just looking at Canvas, of course, there's every creature attacks Sam. There's a solution for that with one quantifier. And then there's going to be a slot 8 every apple for 2 quantifiers. And then there's a few pronoun sentences as well that we'll see. So this is on the truth conditional meaning quantified sentences page. And also, if you want to take a look at these rules again, to see how these predicate logic translations line up with the rules themselves, I've also tried to color code them. So you can take a look at the rule with the color coding and then an actual translation with the sentence. Again, just to reinforce how these are made, because this will help with the tree rules on assignment 6. Okay, are there any questions about this quantifier tree, or if there's anything that you want me to zoom in on for a few seconds? Okay, so let's see what happens when we get 2 quantifiers in a tree, because we're going to get scope ambiguity. So how do we deal when we have to use a rule 2 times? So we're going to use the sentence, every actor knows some skill. So we're not just going to use the word person. We're going to talk about actual objects in this case. So every actor knows some skill. So we have 2 quantified expressions, every actor and some skill. So we're going to have 2 different trees. I've chose every actor as T1 for the subject, so the subject comes first, and some skill as T2 or NP2 because it's the object. So we have the first case where we have the universal scoping over the existential. So that means that let me use blue. It means that the subject moves higher than the object in the first case. And in the second case, the object is moving higher than the subject. So we can see the 2 different tree structures here. So we're going to see how each of these work. And then we have the 2 translations on top. And what we're going to find is that each of these predicate logic translations match the truth conditional meaning translations as well, or truth conditions of the sentence. So one thing that we notice, and we're going to take advantage of in the lecture slides, and I encourage you to take advantage of this too, if you ever come across this, is that in both of these structures, we have some similarities, and that's that everything up to S1 is completely identical. So T1 knows T2 is exactly the same in both of these trees. So there's no reason for us to do this part twice. We might as well just do it once and then just focus on doing these 2 structures separately. So that's what we're going to do. We're going to build that S1 tree on one slide, and then we're going to build two different trees for S2 and S3. Just because, I mean, why bother repeating the same part twice? And it takes up prime real estate on our slides. So let's see how we can do T1 knows T2. And this is really exactly what we did in F1. So now we're just dealing with traces. So we have T1 knows T2. So here's our trace T1 and T2. So, I mean, you've all worked with this with F1. So T2 will be G of T2, which will move up with the tree. We're dealing with the word knows, which is transitive. So it's going to be the set of x, y, such that x knows y. So our VP, we're going to put in the object first, which is T2. So we're substituting in that y position. So we're going to get the set of x such that x knows G of T2. In M, we have a subject G of T1. So our sentence will be true if G of T1 is in the set of x such that x knows G of T2. And this makes sense because we're just saying T1 knows T2. So yeah, this should be true if this thing is in the set of people who know T2. But again, these are not proper names. These are just traces. So these are written as functions. But again, the same thing we've seen multiple times. So this is going to be our base for both of our trees. Does anyone need me to go into this in further detail, or can we just keep going? Okay. Based on test 2 results, I think it's good. I just want to double check. Okay, so this is the all x exists a y tree. I will zoom in. Again, just because we're only dealing with a small portion of the tree doesn't mean it makes the text any bigger, because it's still so much. So here is S2. So this is what we started with. Is it's true if G of T1 is in the set of x such that x knows G of T2 and M. So what we've done in this example is we've moved some skill first. So some skill is lower. So this is NP2. So we know how to do skill because skill is a common noun. So we're going to say that x, or that this is the set of x such that x is a skill in M, and this will be the same for skill and the common noun. Okay, so this is some skill 2, T1 knows T2. So this is nice because this is really just what we saw in the one tree example, or one quantifier example. So it's true if for some D in our universe, D is a skill. This could say NC, but I'm just putting skill in there just so we can make more sense of it right away. And S1 is true where D is replacing T2. So there's some binding happening. So I'm just going to write this out very clearly that G of T2 is now equal to D. So we can make that substitution at this point. So when we spell this out, we're saying if for some D in our universe, so what we're doing here is we're doing the exists a Y, skill Y, and G of T1 is in the set of X such that X knows D. So this is basically saying there exists a Y such that Y is a skill and X knows Y. But this this X is still free. So we still haven't bound X yet. We don't know what the X is, but we know that the Y is a skill. So we're saying like it or they or them, or sorry, he or she or they know some skill. So with the substitutions, really what we've done is we've just replaced G of T2 with D because that's the binding that's occurred. And we've introduced the existential and the skill. So we've just applied the rule that we did before. Now what we're going to do is we're going to introduce the universal with every actor. Okay, and all we're doing is applying the rule again. So it might look like it's a little bit more complicated because we have an extra line, but really nothing here is changing. We're just adding a little bit more to it. So we're doing every actor. So let's just take a look at our little NP1 here. So we're doing NP1 now, every actor. We know what actor is. So actor is a common noun, so we can give it a set, the set of X such that X is an actor in M. This will move up to the common noun. So the set of X such that X is an actor in M. Okay, so we can do this. So when we go up, the first line is going to look very familiar. It's just the rule for S3. So this is the universal rule. So if for all d prime in U, so here now we're using d prime. So we're using d prime instead of d because we've already used d. So let me just make this clear. We've already used d. If you want to use e instead of d prime, you can use e, or you can use c, or you can use some other letter that hasn't been used before. It's just convention in this set theoretic truth conditional meaning to use d prime. Or d apostrophe, whatever you want to call it. It's just usually called d prime. So if d prime is an actor, so if it's in that common noun, again, I'm just putting actor in there so that way we can follow along a little bit better. Then S2, which is the child there, is true where d prime is replacing t1. And again, we're replacing t1 in this case because we're dealing with np1. So np1 and t1, these are linked, so we know which one we're replacing. So what this intermediate step is doing in line 2 is it's basically just filling in the second part while not dealing with S1. So we don't really need to talk about this one, and it doesn't need to be included. But then for line 3, basically in line 3, we're just spelling everything out. So if for all d prime in our universe, so let's just write out the predicate logic translation first. So at this point, we're adding in the for all x. If x is an actor, then there exists a y such that y is a skill, and x knows y. So at this point, the x is now bound because we've introduced the universal x. So if we take a look at our reading, if for all d prime in our universe, if d prime is in the set of x such that x is an actor, then, okay, for some d in our universe, d is a skill, and d prime is in the set of x such that x knows d. So what really has changed here from the line before? Well, we've replaced g of t1 with d prime. And let me just make this box a little bit bigger so you can see for sure there's a d prime there. But if we take a look at the truth conditional meaning and conditions, how it's spelled out, and how the translations go, again, it matches very nicely. So if for all d in our universe, that's the universal right there, if d prime is in the set of X such that X is an actor. So if X is an actor, then it's the conditional. For some D in our universe, there's the existential Y. D is in the set of X such that X is a skill. There's skill Y. And then D prime is in the set of X such that X knows D. So if you think of the D primes as being X's and the D's as being Y's in this example, then it matches the predicate logic translation perfectly.
Could you explain again the second line, the last part of the second line when it says S1 mg and then d prime t1 d over t2?
Yeah, I can go to this one. So let me actually screenshot this one and bring it out a little bit so we can focus it outside of the funkiness. Okay, so what's happening here is this is demonstrating the two bindings that are happening. So the inner part's happening first. So so let me get rid of this line. So this part is saying that first g of t1 is now pointing to d prime. So um, t of 1 or t1 is being bound by d prime, and then the second part here is then happening after, where g of t2 is now being sent to d. So in other words, there's two bindings happening at this stage. T1 is being bound by D prime and T2 is being bound by D. So I'm just including the two bindings there. And this happens at this point in the tree because if we think about C command, sorry for zooming out all the way here, but just to illustrate C command, so NP2 is C commanding all of this stuff, and NP1 is C commanding all of this stuff. So in other words, S1 is being bound by both. So NP2 is doing one set of binding with D, and NP1 is doing one set of binding with D prime. So that middle line is just basically spelling out both of the bindings at once. But that's an optional step in the illustration. Zoom back in on that. Okay, I figured I wouldn't have much time to show, or any time to show the second tree. So we can talk about that on Tuesday. But the second tree is really just the same thing as this one, but the order in which we do the rules is different because instead of doing some skill first and then every actor, first we're doing every actor and then some skill. So the truth conditions really look the same in the end, but instead of doing for all D prime and then for some D, we're doing for some D prime and um, then if for all D, then blah, blah, blah. And we'll see that on Tuesday. On Tuesday also, just to show you a little preview of what we're doing, we're also going to see on Tuesday how to deal with pronouns. So we'll talk a little bit more formally about what a free inbound pronoun is, um, how traces relate to pronouns, and how we can do free inbound pronouns in trees. We probably won't have enough time to do the practice questions. Well, maybe we will, but those all have solutions on Canvas too. And that'll be the end of truth conditional meanings of quantified sentences. But we'll start the lecture by looking over the second variant of the scope ambiguous sentence. So that is it for today. If you have any questions, you're free to stick around and ask. Other than that, enjoy the weekend. Good luck on the assignment. And if you have any questions, feel free to bug me over email or on Canvas or wherever you want. And if you want me to zoom in or go to another previous slide before you leave too, feel free to ask. But yeah, enjoy your weekend.